We're getting into something really, really fundamental. Electric charge.
Absolutely foundational.
Yeah, and specifically, we want to dig into the difference between positive and negative charge. We've got all your source material here, and our job, really, is to pull out the key ideas, make this core concept clear.
Make sure you walk away feeling, really solid on this.
Exactly.
And it's important because, positive, negative, they sound simple, right? Almost basic.
Right.
But why we have that distinction, what it actually means, that's crucial. Your sources really show it's the bedrock for how matter interacts.
It drives electricity, magnetism.
Everything from tiny atoms all the way up to massive lightning bolts.
Yeah.
And the details in your materials, they're pretty fascinating when you get into them.
They really are. We're going to find out, based on what you've given us, things like the history behind the names, kind of surprising, actually. Who carries these charges, and how these simple plus and minus signs basically run the show with forces. It's all coming straight from the info you provided.
Yeah, think of us as just helping you connect the dots in those sources.
Okay, sounds good. Let's unpack this, starting right at the beginning. What is electric charge, according to these sources?
Okay, so your material defines it as a fundamental property of matter.
Fundamental, okay.
Yeah, it's this intrinsic quality that makes something feel a force when it's in an electromagnetic field.
Ah, okay, so it's built into the smallest pieces of stuff.
Exactly, the elementary particles, the building blocks of everything.
Got it. And the sources stress there are just two types, positive and negative.
Just the two.
But why those names? Is there some deep physical reason it had to be positive and negative?
Well, that's one of the first really interesting points in your sources. It actually comes down to history, a convention.
A convention, not physics.
Well, the physics is real, but the names point back to Benjamin Franklin.
Franklin, like lightning kite Franklin.
That's the one. He was working on this stuff centuries ago, and he had this idea, this theory, that electricity was like a kind of invisible fluid.
A fluid? Seriously, like water?
Sort of, yeah. An electrical fluid. And his thinking, based on experiments like, rubbing things together.
Static electricity.
Right. His idea was if an object had too much of this fluid, an excess, it had one type of charge. If it had too little, a deficiency, it had the other type.
Okay, so more fluid, less fluid.
Exactly. And then he just kind of arbitrarily called the state of having excess fluid positive and the state of having not enough negative.
Well, hang on. So he just picked the names. It could have been A and B or up and down.
Pretty much. The fluid idea itself, we know now that's not how it works. But his labels, positive and negative, they stuck.
That's amazing. So we're using terms based on an outdated model.
We are. And the modern definition, which your sources laid out, is tied directly to that convention, but linked to electrons.
Ah, okay. So how does it work now?
Now, based on Franklin's choice, we define positive charge as what happens when an object has a deficiency of electrons, meaning overall it has more protons than electrons.
Okay, fewer electrons means positive. That links back to his deficiency idea.
Exactly. And negative charge is defined as having an excess of electrons, more electrons than protons.
More electrons means negative, like his excess fluid.
Wow. So the names are historical, but the definition is now precise based on that electron balance.
That historical context from the source is really helpful. It explains why these specific words... Okay, so it hinges on electrons. But who are the actual charge carriers at the particle level?
Right. So zooming into the atom, your sources point to two main players, protons and electrons.
And they're different in where they live and what charge they have, right?
Totally different. Protons are packed into the atom's core, the nucleus.
Dense center.
Very dense. And each proton carries one single unit of positive charge. We call this the elementary charge and label it plus E.
Plus E. And E is like the basic unit, the minimum amount.
Yeah, E is essentially the smallest chunk of free charge you typically find. Your sources give the exact number, it's tiny, but the concept is key. It's the fundamental unit.
Got it. Okay, so positive protons in the middle, electrons.
Electrons are the ones buzzing around the nucleus in those shells or orbitals you hear about.
Lighter, faster.
It's much lighter, yeah. And each electron carries one single unit of negative charge, which we write as E.
Minus E.
And here's a really crucial point your materials emphasize. The size, the magnitude of the electron's negative charge is exactly the same as the proton's positive charge.
Wait, exactly the same amount of charge. Just one's plus, one's minus.
Precisely. Equal in strength, opposite in sign. That equality is incredibly important.
That is fascinating. Okay, and what about neutrons? They're in the nucleus too, right?
They are hanging out with the protons, but as the name kind of tells you, neutrons are neutral.
No charge.
No net charge at all. So they add mass, but they don't affect the atom's overall charge balance between the positive protons and negative electrons.
Okay, that setup, positive nucleus, negative electrons, leads directly to maybe the biggest difference, how these charges interact.
Yes, the electrostatic force. This is absolutely central, and your sources spell it out very clearly. It's a simple rule, but it governs so much.
Okay, what's the rule?
Like charges repel each other, opposite charges attract each other.
Simple as that. So two positives, push away.
Repulsive force, yeah,
No?
pushes them apart.
Two negatives.
Same deal, repel, push away.
But if you have a positive and a negative near each other,
They pull together. An attractive force.
uh,
And your sources really stress this isn't just some abstract rule, this attraction and repulsion. It's why chemical bonds form.
holding molecules together.
Exactly. It's why static electricity makes a balloon stick to the wall. It's fundamental to pretty much all of chemistry and electricity.
That simple rule has such huge consequences. Okay, another really important idea your sources dig into is about charge itself. Can you have like half a charge? Or is it lumpy?
That's the concept of charge quantization. And yeah, your materials make it clear. Charge is lumpy. It's not continuous like pouring water.
Not smooth, but like steps.
Stepped is a great analogy. It comes in discrete packets, distinct chunks.
And how big are the chunks?
The size of the chunk, the smallest step, is that elementary charge we talked about, the magnitude of charge on a single proton or electron.
Back to E.
Always back to E. So any charge you can actually measure on an object anywhere in the universe is always a whole number multiple of E.
Meaning like +1 or -5e or +200e.
Exactly. But never, ever something like plus 0.5e or -3.14e just floating around freely.
But hang on, the sources mention quarks, right? Don't they have fractional charges?
They do mention quarks, yes. Good point. Quarks have charges like plus or minus 1/3 or plus or minus 2/3.
So that breaks the rule.
Not quite, because as your sources are careful to point out, you never, ever find a quark by itself. They're always stuck together inside other particles like protons and neutrons. And when they combine, the total charge of the resulting particle, the proton or neutron, always adds up to an integer multiple of E, like 0e for a neutron or plus 1m for a proton.
So the fractional charges are hidden inside, but the particles we actually see always follow the integer multiple of E rule.
Exactly. For all practical purposes, observable charge comes in steps of E, quantized.
That quantization is a really key detail from the sources.
Right.
Okay, so thinking about bigger things now, not just single particles, like everyday objects. How does positive and negative work there?
Right, because objects are made of trillions and trillions of atoms.
Yeah.
So we talk about the net charge. An object's net charge is just the grand total, the sum of all the positive charges from its protons minus all the negative charges from its electrons.
Just adding them all up, consider the
Yeah,
signs?
yep, the algebraic sum. So if an object happens to have more protons than electrons overall,
More positive than negative.
then it has a positive net charge. The total positive outweighs the total negative.
And if it has picked up extra electrons, so it has more electrons than protons.
Then it has a negative net charge. More negative charge than positive.
Simple enough. And if the number of protons and electrons is exactly equal,
That's electrical neutrality. The total positive charge perfectly cancels out the total negative charge. The net charge is 0.
and the sources say most stuff is usually neutral.
That's right. Most matter you encounter day to day on the macroscopic scale is electrically neutral because atoms naturally have an equal number of protons and electrons.
Okay, but objects can get a net charge. You rub a balloon on your hair, it gets charged.
It does.
So where does that charge come from? Or where does it go? Can charge just pop into existence?
No. And that brings us to another really fundamental principle your sources highlight. The conservation of charge.
Conservation meaning it doesn't change.
Exactly. It states that the total net electric charge within an isolated system, a system cut off from the outside, always stays the same. Constant.
You can't just create charge out of nothing or destroy it.
Not in isolation, no. Charges can only be moved around, transferred.
So when you rub that balloon and it becomes negatively charged.
Your sources explain that means it gained electrons.
Okay.
But those electrons had to come from somewhere. They came from your hair.
So my hair lost electrons.
Making your hair become positively charged, the total charge between the balloon and hair system stays the same, it just gets redistributed.
So becoming positive means losing electrons. Becoming negative means gaining them.
That's the mechanism. Electrons get transferred. Now, there is a nuance. Charge can be created or destroyed, but only ever in positive-negative pairs.
Like matter and antimatter.
Exactly, like creating an electron EE and a positron plus E together out of energy.
Right.
The net charge created is 0. E plus E equals 0. So even then, the total charge of the system doesn't change.
It's always balanced. The total amount of positive minus negative in a closed system is fixed. That's a really powerful idea from the material.
It's a cornerstone of physics.
Okay, and these charges, positive and negative, they don't just sit there. They affect the space around them, right? Fields.
They do. They create electric fields. And again, the positive-negative difference is key here.
How so?
Your sources explain that the convention, the way we draw these fields, is that electric field lines start on positive charges and end on negative charges.
So positive charges are like sources, spewing field lines out.
That's a good visual, yeah. Radiating outwards.
And negative charges are like sinks, where the lines terminate, pointing inwards.
Exactly, for isolated charges.
Yeah.
And if you put another charge in that field, it feels a force.
Right.
If you place a tiny positive test charge in the field, it gets pushed in the same direction the field lines are pointing.
Following the lines away from the positive source towards the negative sink. Makes sense.
But if you put a negative test charge there...
It goes the other way, against the lines.
Precisely. It gets pushed opposite to the direction of the field lines because it's repelled by the negative end and attracted to the positive source.
Opposite behavior again. And this relates to electric potential too, doesn't it? Like voltage.
Directly. Your sources detailed this. Positive charges naturally want to move from places of higher electric potential to places of lower electric potential, like rolling downhill.
High potential to low potential for positive.
But negative charges, they do the opposite. They naturally move from lower electric potential towards higher electric potential.
Uphill, in that analogy.
You could think of it that way, yeah. And it's this difference in potential, this electrical pressure that drives current electricity, the flow of charge, usually electrons, in a circuit.
Wow. So many differences in behavior, all tracing back to that plus or minus sign. Maybe we should quickly recap the main distinctions the sources pointed out.
Yeah, good idea. So key takeaways from your materials. The carriers are different protons, positive, electrons, negative.
Equal magnitude, opposite sign. Critical point.
Absolutely.
Yeah.
The names themselves, positive, negative, are just a historical convention tied to electron deficiency or excess.
Thanks to Franklin.
Right. Their interaction is fundamentally opposite. Likes repel, opposites attract.
The basis for so much.
Mm-hmm. Then there's their movement in fields. Positives go with the field lines, negatives go against them.
And potential.
Positives move from high potential to low, negatives move from low potential to high.
Getting charged is opposite too. Losing electrons makes you positive, gaining makes you negative.
And even visually, the field lines point outwards from positive, inwards towards negative for isolated charges. It's opposition at every level described in the sources.
It really boils down to that fundamental duality, doesn't it? Equal charge strength, but opposite signs, leading to completely different behaviors.
Yeah.
That really seems like the core message from your sources.
That's the heart of it, absolutely. And understanding that opposition, which seems simple on the surface, is just essential. It's not just textbook stuff. It unlocks why the electromagnetic world works the way it does, governing stuff we see, well, every single day.
Right. Okay, let's bring it home. Why does this positive-negative thing matter so much ultimately?
Because, as your sources consistently show, these basic rules, opposite signs, opposite behaviors, they underpin how the physical universe operates at a really deep level.
Yeah, I mean, we set out to get clear on positive versus negative charge using your source material, and we've hit on the history, the particles,
Protons, electrons,
the attraction-repulsion rule,
social,
quantization. The fact charge comes in chunks.
Can't forget that.
How net charge works. The conservation law that charge isn't created or destroyed, just moved.
Or created, destroyed in pairs.
Right, pairs. And how they act differently in fields and potential. And we really tried to pull out those key nuggets from the sources for you.
And hopefully give you a few of those aha moments along the way, connecting the dots from the material provided.
Definitely. And maybe here's a final thought, something for you to chew on. Think about that simple rule. Opposites attract, likes repel. It seems so basic, but that single interaction is driving forces you experience constantly. Static cling when you pull clothes from the dryer, right? Dust sticking to your TV screen. But even more profoundly, it's a key part of the force holding the atoms in your own body together.
It really is that fundamental.
So maybe look around. What other everyday things can you now see a little differently, knowing this simple plus-minus opposition is working underneath?
It's worth thinking about. Keep questioning.
Absolutely. Thanks so much for joining us on this deep dive. Keep that curiosity sparked.